As you have seen, one category of improper integrals deals with infinite limits of integration. Another form of improper integrals is not quite so obvious. These involve integrals with infinite integrands. That is, the integrand itself will have an infinite discontinuity. Remember, infinite discontinuity is code for vertical asymptote. This vertical asymptote will occur somewhere between the limits of integration. For example, suppose that we consider number 1, the integral from a to b of f of x dx. The initial presentation of this integral does not catch our attention much. It looks like an ordinary integral. However, we're assuming that this function f of x has an infinite discontinuity at the lower limit of integration. That is, it begins on a vertical asymptote. So if we look at the graph, let's suppose f of x is represented by this black curve, and we want to evaluate the integral from x equals a, where we have a vertical asymptote, to some finite value x equals b. Well, we're going to rewrite the integral using a limit operator. We're going to introduce a new lower limit and allow c to approach that vertical asymptote from the right. That will give us the necessary notation to correctly evaluate the integral. Now, another thing that can happen, the vertical asymptote may occur at the upper limit of integration. So again, looking at the graph on the right, let's assume the black curve represents f of x, and there is a vertical asymptote at x equals b, or an infinite discontinuity to x equals b. And we want to find the integral from some lower limit a up to this vertical asymptote. Well, we're going to use a placeholder, a new placeholder for the upper limit of integration, and we're going to allow c to approach b from the left. So we are approaching that vertical asymptote from the left. Again, the limit operator gives us the necessary notation to correctly evaluate that integral. Now, one other possibility is you are dealing with an ordinary looking integral from a to b of a function f of x dx. However, somewhere between a and b, there is a vertical asymptote in that function f of x. So what we're going to do is split the interval from a to b to the left side of our vertical asymptote and the right side of our vertical asymptote. So we're going to integrate from a to c. That's going to calculate the area on the left, and then we're going to integrate from c to b. That's going to calculate the integral on the right. Then, because there is that vertical asymptote at c, we would adjust both integrals accordingly using proper limit notation. So let's give this a try on a couple of examples. Notice that the integral from 0 to 3 of 1 over x minus 1 raised to the 2/3 power dx, it looks like an ordinary integral. It doesn't catch my eye as being improper. However, notice that the interval of integration is from 0 to 3, and by the looks of the factor in the denominator, we can say there exists, remember the backwards e means there exists a vertical asymptote, I'm just going to call it VA, at x equals 1. 1 is in between my interval of integration. So this is an improper integral because we're integrating over a vertical asymptote. So we need to make it proper. So we're going to take our integral from 0 to 3 and we're going to split it to the left of that asymptote and to the right. So we're going to split it up as the integral from 0 to 1 of 1 over x minus 1 to the 2/3. And then we're going to add that to the integral from 1 to 3 of 1 over x minus 1 to the 2/3. In order to execute this in a legal way, we do need to introduce our limit operator around that vertical asymptote. So we're going to have a new upper limit. We'll call it b. We're going to approach 1 from underneath or from the left. So we can write this as the integral from 0 to b of 1 over x minus 1 to the 2/3 dx. Similarly, We will introduce a new limit operator on our second integral, and we will approach the lower limit a from above or from the right. So we have the integral from a to 3 of 1 over x minus 1 to the 2/3 dx. Now, both of these integrals will be handled in the same way. Notice if we let u be x minus 1, du would be dx, and we can think of the integral as x to the negative, u to the negative 2/3 du. When we integrate u to the negative 2/3, we would end up with 3u to the 1/3, or u to the 1/3 divided by 1/3, which of course simplifies to 3u to the 1/3. So ultimately, we would end up with the limit as b approaches 1 from the left. Replacing u with x minus 1, we'd have 3 times x minus 1 to the 1/3, evaluated from 0 to b. And the limit as a approaches 1 from the right, same antiderivative, 3 times x minus 1 to the 1/3, evaluated from a to 3. Let's plug in our upper and lower limits of integration. So here on the first one, we're going to start by plugging b in for x. There's our upper limit. And then we'll plug 0 in for x. We'll apply that same process to our second expression. Our upper limit is 3 this time, and our lower limit is a. Starting with our first term, as b approaches 1 from the left, this expression will go to 0. And similarly, as a approaches 1 from the right, this expression also goes to 0. So we are simply left to evaluate this constant and this constant. So finding a little spot up here, a little space, we have negative 3 times negative 1 to the 1/3 plus 3 times 2 to the 1/3. Well, negative 1 to the 1/3 is negative 1, so my first term is 3. And 2 to the 1/3, you can also think of that as cube root of 2, and that would be a great way to answer that value exactly. These improper integrals, again, can sneak up on you. It helps sometimes to examine the graph really to know exactly what's going on. In this case, we would have had a vertical asymptote at 1. So in this case, the graph does something like this around that asymptote at 1. So we have found the area between the curve and the x-axis from 0 to 3. So the fact that our integral turned out to have a finite value tells us that that area is finite, which is really interesting around that infinite discontinuity. Let's consider another example. And remember, these are unassuming. They don't catch your eye like those that have infinite limits of integration. You got to really be watching for these. Example 7. Find the area between y equals cosine of x over the square root of 1 minus 4 sine squared of x dx between that curve and the x-axis over the closed interval from 0 to pi over 6. Now recall that sine of 0 is 0, so we don't have a 0 in the denominator at the lower limit of integration, but notice at pi over 6 what happens to this integrand. Sine of pi over 6, we can get this from our unit circle, is 1/2. So when I evaluate the denominator at pi over 6, I end up with 0. So we have a 0 in the denominator at what we will define to be the upper limit of integration. So we're going to have to correctly notate that with a limit operator. So we'll begin by setting up the problem as the integral from 0 to pi over 6 of cosine of x divided by the square root of 1 minus 4 sine squared of x dx, and correct it with our limit operator. So we'll define this as the limit as b approaches pi over 6 from the left of the integral from 0 to b of our given integrand. To execute the integration on this particular problem, we'll make a u substitution. We can let u be sine of x, then clearly du will cover up that numerator, cosine of x dx. So let's rewrite our integral in terms of u. As always, when we make a variable change, we need to be very careful with our limits of integration. Recall that pi over 6 was an x value. When x is pi over 6, u will be sine of pi over 6, and sine of pi over 6 is 1/2. So I need to change the value of this limit. We're going to let b approach 1/2 from the left. Similarly, when x is equal to 0, sine of 0 is 0, so my lower limit will stay 0. The integrand then becomes 1 over the square root of 1 minus 4u squared du. Now, by the looks of this integrand, we're going to need to evaluate this with trigonometric substitution. So, following our standard guidelines for what we choose for the trig substitution here, we can say 2u is a, or 1 sine theta. Then 2 du is cosine of theta d theta, or du is 1/2 cosine of theta d theta. So this is a pretty technical integral. We're changing variables again, which means we need to double check this value. This was a u value. If we plug 1/2 in for u, we can see sine of theta equals 1, and that occurs at pi over 2. So once again, I'm going to change that limit of integration to pi over 2 from the left. The lower limit of integration once again stays the same. So we have the integral from 0 to b of 1 over the square root of, now notice this is 2u squared, 1 minus sine squared theta, and du will replace with 1/2 cosine theta d theta. We'll recognize in the radical in the denominator, we have 1 minus sine squared theta. That's equal to cosine squared of theta. And the square root of cosine squared of theta is cosine of theta. So when we simplify this radical, it's going to cancel this factor here. And we get a very simple integrand, 1/2 d theta. Of course, the antiderivative of that is 1/2 theta. And we'll run this from 0 to b. Almost there. Hang in there. We have 1/2 b minus 1/2 times 0. Of course, that last term's the easy one to handle. It has a value of 0. And when we plug in pi over 2, we have 1/2 times pi over 2, or pi over 4. Recall that we were finding the area between the curve and the x-axis, so let's indicate that we just determined a two-dimensional area by including pi over 4 units squared. So the area between that curve and the x-axis from 0 to pi over 6, where we have a discontinuity at pi over 6, is finite, and we calculated exactly pi over 4 square units. Now, that was a technically demanding problem. It not only required us to recognize that discontinuity and make the improper integral proper with the limit operator, but we had to change variables twice. We went from x to u, and then we went from u to theta. So each time we change variables, we're also updating our limits of integration. But that is an interesting problem, and again, one that really demonstrates your technical Calc 2 skills. So good job on that one. By the way, this completes the information for Chapter 8. So we are finishing up our study of integration here in Calculus 2. So that's another good milestone that you can celebrate.